Salts can dissociate into more than 2 ions. So like calcium chloride will dissociate into 1 calcium and 2 chlorides. These are the 2 salts that we salt the roads with. We're going to see in a little bit that we talked about colligative properties. You can depress the freezing point of something by adding molecules. Ions are even better because each ion is its own colligative particle. So calcium chloride counts as 3 particles, not 1, because it breaks apart into 3 ions. When we salt the roads, they always use sodium chloride and calcium chloride. Why these 2? What are the advantages of these 2? They dissolve easily, and they are not poisonous, which is key. One's if kids eat the snow. One's if your dog eats the snow. So you can't be dumping something poisonous on city streets. And so, this is table salt. The human body can deal with a lot of salt before it's dangerous. And calcium chloride, your body can use calcium. Even if you're getting too much calcium, you'll start storing it in your bones. And so, it would be really, really, really difficult to overdose on calcium. I mean, everything is theoretically doable, but this would not be easy. And so these are really safe salts to use.
Yeah, but they ruin your cars over a time period. Like Iowa, you're not going to find one older Dodge or Chevy or Ford pickup that ain't rusted out. And
you're right.
A little bit of that's because of the...
It is because of the salt. Absolutely, because the salt water splatters on your car, and that's a conductor. Yeah. So rusting is an oxidation reduction reaction. So it's going to happen a lot faster, you're right. Things touching ocean water rust a lot faster. And that's why we talked about those sacrificial anodes earlier when they strapped all those blocks of magnesium onto nuclear subs, because otherwise it would rust out because it's in salt water. Yeah, but in cars they'll say California condition
I was just going
to signify that it's never experienced salty water ever. Because like that just means it never snows in California. So no one has any need to put salt on the roads, and that's where the term came from.
You can buy cars from there in a pristine condition, like older cars. Oh man.
Yeah, your cars are going to last a lot longer out there just because they're not going to rust anywhere near as quickly. Same thing in the South, like when you trade in a used car battery to get a new one, they sell it down south, these batteries. Because what you really worry about is cold weather. Like if your battery is weak, it's going to die when it's cold. Cold weather is hard on batteries. But if you sell it like in southern Mississippi, where it's never going to get that cold, a battery that would have failed in Iowa this winter might last 5 more years for you. So you can use it down there. You just don't need the same kind of load on those batteries. And so yeah, northern climates are harder on cars. There is no doubt about this.
There's nothing we can do either. There's nothing like, you can't put things on your cars to help them not do that.
Well, no, you'd have to like somehow cover your entire bottom to not get spatter up in there. But that's why like for some cars, people store them in the winter.
Right.
You know, because that way you can just avoid the whole season. And generally you wait for a good rain in the spring before you take it out of the garage. Because that way it'll rinse off any salt residue that's still on the highway. And that's the way I mean, obviously that's not going to be like a daily driver, because then what would you do in the winter? But for like a second car, definitely you have to do that in northern states.
It's like this brown stuff. They put the brown, like in Spencer, they put rock or something. It's like minus, huh?
Wait, are you talking about on the road?
Yeah, something on the road in the winter. It's brown. It's not like
sand.
Yeah, it's sand. So why don't they just can't that break apart some of that stuff, or does it not have that kind of?
Sand will give you more gription, but sand won't dissolve in water, and so it's not going to give you the freezing point depression.
Oh, so
and so it's not going to work as well.
Yeah. Well, as I say, because I know they not only put it by the stop sign before you stop, but they salt a lot of the roads just for traction. But I didn't know if that could help break it down or not. I didn't think so, but that's why we have to use salt.
Yeah. The salt will actually help melt the ice, because as it dissolves into the water, it keeps lowering the freezing point.
Yeah.
Or even if it's -10 outside, if that salt water's freezing point is -20, it'll still be liquid.
Yeah.
And so
hopefully we'll find something better to use in a few years.
And it works because cars are so heavy. Because when you apply pressure to ice, it momentarily melts, like when you're ice skating. And when it's in that momentarily melted state, the salt dissolves in, and then it's dissolved.
Yeah.
And so you pretty much, you dump the salt on it, and you wait for the cars to drive over it, and it'll keep melting it. What is the concentration of bromide ion in a 1.5 molar solution of magnesium bromide? Well, that's MgBr2. So you'll get 2 moles of bromide for every 1 mole of magnesium bromide, meaning it'll be 3 molar. And again, the biggest difference with colligative properties is each ion counts as a colligative particle. And so for calcium chloride, once you have the molality, like we found in chapter 14, then you times it by 3, because calcium chloride is 3 colligative particles. Calcium plus 2, and then Cl minus, and then the other Cl minus. And so ions have much more colligative properties, because each ionic particle acts as its own colligative particle. So calcium chloride will raise the boiling point or depress the freezing point 3 times as much as an equivalent molality of sugar or something else that doesn't dissolve. What is the boiling point of 2 molal aqueous sodium chloride? Well, it's 2 molal, and then we have to times it by 2 because you get a sodium plus and a Cl minus. So it's actually 4 molal for ions. And then we times it by the Kb, and we get a boiling point elevation. Pure water also self-ionizes to a very, very, very small extent. And so if I gave you 100% super deionized pure water, your H plus concentration would be 1 times 10 to the negative 7th molar, which is like 1/10 of a millionth of a mole. Very small. So a very, very, very small number of water particles will break apart into H plus and OH minus on their own. The concentration of H plus times the concentration of OH minus will always be equal to 1 times 10 to the 14th. That is the water constant. So if you know the H plus concentration, you can find the OH minus. If you know the OH minus, you can find the H plus. The one time they're both equal is when they're both 1 times 10 to the negative 7th. And that's pure water. In pure water, your H pluses and your OH minuses are exactly equal to each other because they came from a water molecule breaking apart on its own. Because there's a little bit of self-ionization happening. So that's when you have a purely neutral solution, those 2 numbers are equal to each other. In acidic solutions, the H plus concentration is way higher than the OH minus concentration. And in basic solutions, the OH minus concentration is a lot bigger than the H plus concentration. And this is when we take the pH, that's the power of hydrogen, negative log of H plus. And in purely neutral water, the H plus concentration is 1 times 10 to the negative 7. You take a logarithm of that, you get negative 7. You times it by negative 1, and you get 7. And this is why completely neutral water has a pH of 7. Because in completely neutral water, both the H plus and the OH minus concentrations are 1 times 10 to the negative 7. So you take a logarithm, the negative logarithm of that, and you get 7, which is exactly neutral. Completely, totally, pure neutral. The pH scale does not end at 0 and 14. That's just a common scale they use. But like if you put in your calculator, like we buy hydrochloric acid concentrated, it's 12 molar. If you take negative log of 12, you're going to get a negative answer. And so you can have a pH of negative 1. You can have a pH of negative 2. That just means it's ridiculously, insanely acidic. But it's possible. Likewise, if we had 10 molar NaOH, we'd have a pH of 15. So you can have a pH of 15 or 16. It just means it's extremely basic. And so there are no limits to the pH scale. It's just 0 to 14 is your normal spread. But you can go outside of that. It's just rare because you need a really, really strong compound to do that. So pH of less than 7 is acidic. pH of greater than 7 is basic. And here we see some common things that are these pHs. Gastric juice, that's your stomach juice, pH of 1. So is 0.1 molar hydrochloric acid, which is 100 times weaker than what we buy from the store. Because what we buy from the store is 12 molar. And so your stomach acid is 100 times weaker than the chemicals that we buy for our lab that we dilute down and use. Lemon juice, 2.3 from the citric acid. Same with lime juice would be very similar. Then we have vinegar at 2.8. Orange juice, 3.7. Tomato juice, 4.1. Black coffee, 5. Urine, 6. Milk, 6.6. Pure water, 7. Blood is just a little basic, 7.4. Ammonia, 11. And then 1 molar lye, 14. So, what's up, Ashley?
Who drinks black coffee?
Yeah.
So,
Gross.
what's wrong with
It's
that?
actually
Do you,
good for
do you
you.
like black coffee?
If it's good coffee, yes.
Oh my god.
No, when the coffee is black coffee, then it actually matters what the quality of the coffee
Yes.
is. And so, if you're gonna like pour a bunch of sugar in there and a bunch of creamer in there, I mean, you might as well buy the cheapest coffee possible
Yeah.
because like you're getting so much other stuff, you won't be able to appreciate the coffee anyway. Like it's like a candy version of it, which is fine. But like if you want to taste the coffee, then black
See,
is
I was gonna
definitely the
say-
way to go.
My fiance, he gets the bag of the beans.
Yeah.
And then he'll grind them up and then make coffee that way.
All right.
See, some of it's good, you just have to try it. Yeah.
I like that. I don't know, I guess I'm weird, so I'm not much of a coffee drinker, but I'll drink the Starbucks. They got the bottle of like the hard, it's called like, they just came out with this salted black chocolate. It's ice brewed or whatever.
Sounds good.
It's delicious. I should have brought it in here, but yeah, it's really good. I've never really been a coffee drinker, but my boyfriend likes them once in a while, so I tried them.
Yes,
And now
awesome.
they came out with some new ones. And
You're
so,
like-
they came out with a white chocolate, like it's toasted white chocolate is what it's called.
Yeah.
So it gets you with the words, like the wording, and then you try it. It's so good. And then the salted dark chocolate's a little stronger, but man, it's like good. Then they got caramel and vanilla in there.
So they're popular. Like, even in really small towns, you can find a Starbucks. Like,
They're only expensive though, because they're three.
They are
they're
expensive.
Like, I think they're $3 a bottle, but the bottle is what costs the money, not the actual coffee. Because the bottle is like glass, and it's heavy duty glass, so it costs more.
no, glass isn't that expensive.
Well, they make it that expensive because they're weird like that.
That's profit. Glass bottles are definitely not expensive. In fact, ironically, in a lot of more poor countries, like pop is almost always in glass bottles.
Yeah, but it's pretty good. Give it a try. It's at local gas stations. It's pretty good. It's like cold. It's all cold.
Oh, you mean like the pre-made bottle you can buy?
Yes.
Yeah. Okay, I thought you meant
It's
I
like,
mean, like a
going-
Starbucks, like a one step.
Yeah.
I'm sure you could go and get it the same stuff from Starbucks, but no, I get the actual like already pre-made stuff.
Right on.
I'm weird like that. I
It's
just,
more expensive if you actually get it from
The store, yeah.
oh yeah.
just for like, you're basically paying for ice. Like if you get like.
Yeah,
iced
seriously.
coffee,
No, I
it's
refuse
like-
to get iced coffee there because you're
Well,
right.
ice.
Half of your cup is ice.
Yep.
There is no way to spend $6 on
Yeah,
coffee.
you're paying like $5, $6 for a cup of ice.
Yeah, pretty much. And then a little clear.
All right, pH was logarithmatic, which is a factor of 10. pH is the opposite of the exponential function. 10 to the second power is 100. The log of 100 is 2. Or I could say 10 to the third power is 1,000. The logarithm of 1,000 is 3. So it's the opposite function to the exponential function, but it's base 10. And so with pH units, every time you move one pH unit, it's 10 times more actually. So pH of 5 is 10 times more acidic than pH of 6. pH of 5 is 100 times more acidic than pH of 7. So pH of 3 is 2 units, so that's 10 to the second. It's 100 times more acidic than pH of 5. So every time you move one pH unit, it actually got 10 times more acidic or basic, depending on which direction you're moving in.